Hello and welcome to another slide video from the Cornish Radio Amateur Club, and today we're going to be looking at biasing bipolar transistors. Okay, so we remember that the transistor is a current amplifying device, and we're going to have a look here at a sample circuit. We remember that the base emitter needs to be forward biased for collector current to flow. So on the left hand side you can see a potentiometer, and I've labelled it there between 0 volts and 10 volts. So if you can imagine that as perhaps the carbon track of a potentiometer, and with various points there starting at the bottom with 0 volts and increasing by 1 volt increments up to the 10 volt rail. So the transistor there has a load in the collector circuit. We've called that RC for resistor in the collector circuit, and two voltages will be developed on the right hand side: a voltage across RC, which will be dependent upon the amount of current flowing through RC, and a voltage across the collector emitter, which will also be dependent on the voltage flowing through the collector emitter circuit. So we will need to have the transistor biased for current to flow. So if we start off then, and we're going to also simultaneously draw a graph of collector current versus base emitter voltage. And if we start off with the base set at 0 volts on the potentiometer, no current will flow, and therefore we would plot that point on the graph. Because no current is flowing through the transistor, no voltage will be developed across RC. And if no voltage is developed across RC, then Kirchhoff tells us that the remaining voltage has got to be developed across the collector emitter of the transistor. So with the transistor switched off, the full rail voltage is developed across the collector emitter. If we increase the potentiometer such that the base voltage is now half a volt, we will see some current just starting to flow perhaps in this NPN transistor. And with the current flowing, perhaps we will see 1 volt, and this is an arbitrary value that just might be a valid example, not based on any maths or anything, but we might see 1 volt developed across the collector resistor. And if this is the case, then Kirchhoff again tells us that 9 volts will be developed across the remainder of the circuit, in other words, the collector emitter. And if we continue to increase the potentiometer, now we're seeing some substantial current flowing through the transistor, because we've increased the base voltage to about 0.7, and we're seeing the knee of the curve. And this IC VBE curve is something we should be able to draw from memory. So now we're seeing some substantial current flowing through the transistor, and therefore through the collector resistor. So maybe we're seeing 5 volts developed across the collector resistor. And once again, Kirchhoff says that will mean 5 volts will be developed then across the collector emitter. And as we continue now, IC becomes fully established as perhaps we go up to 1.5 volts. And perhaps we're seeing 8 volts across the collector resistor, with only 2 volts remaining across the transistor. So that's a picture we should be fairly familiar with. An NPN transistor in common emitter mode with a biasing circuit, a graph showing increases in VBE driving increases in IC, and with a knee in that curve at about 0.6 or 0.7 of a volt for a silicon transistor. Let's have a look at that circuit again, drawn slightly differently. This time we've drawn a potential divider with a fixed resistor R1 and a variable resistor VR1, and that is providing bias for the base. And by altering VR1 we will get that curve which we are so familiar with. When VR1 is set to 0, the base will be grounded and we will see no current. And as we increase VR1, gradually the base will increase in voltage until we get to somewhere like 0.6 or 0.7. We will see the knee and then increasing IC as we continue to turn the knob. If we add a capacitor to that potential divider and put a 1 volt peak-to-peak signal on it, let's see what the picture will be like at point A. So we'll strip away the rest of the circuit, we'll strip away the transistor and everything in orange, and just look at the left-hand part of the circuit as we would see it perhaps on an oscilloscope. Now, if you're unfamiliar with oscilloscopes, I would recommend you have a look on YouTube. There are plenty of videos there showing how to basically operate them. But what we have is essentially a screen, and a little dot will move from left to right across the screen, and at any instant the height of the dot above the 0 volt line will represent the voltage. If it's a positive voltage, the dot will be above the line. If it's a negative voltage, it'll be below the line. So with VR1 turned right back, so it's effectively a short circuit or 0 ohms, then if we apply 1 volt peak to peak on the other side of that capacitor, we will see the swing developed around the 0 volt line. In other words, the signal, the 1 volt peak to peak signal, will go plus half a volt and minus half a volt, and you can see that on the screen. Plus half a volt meaning 1 graticule division, and minus half a volt being 1 graticule division in the opposite sense. So there's a signal swinging around the 0 volt line, going plus a half and minus a half, in other words 1 volt peak to peak. If we now turn VR1 such that we have 1 volt DC level at point A, the signal will then swing to plus 1.5 volt and plus half a volt. So it'll swing between plus 1.5 volts back down to plus half a volt. In other words, it'll swing plus and minus a half a volt around the 1 volt DC level. And similarly, if we turn up VR1 such that there is 2 volts on A, that will be the picture. The signal will go to 2.5 volts maximum and 1.5 volts minimum. Now let's put the rest of the circuit back in and also show a similar depiction on the output. So the green circle on the left is the one we've just been looking at. That's the input. And the bluish circle on the right is the output. And you can see the scales are different. On the output circuit, it's between 0 and 10 volts is shown because that is the rail on our example circuit. And the thumbnails at the top and the bottom there are for reference. Thumbnail at the top is the ICE VBE graph, which we should be able to draw, showing the knee at about 0.6 or 0.7 volts. And the thumbnail at the bottom is our test circuit with a potential divider and our NPN transistor. And if we set the voltage at point A to be 0 volts, then the signal at the input will be like that, and the signal at the output, point B, will be a steady 10 volts. Let's focus in on those two areas. The input we've already explained. Because the voltage at point A is 0 volts DC, the swinging signal applied to the input circuit there will take that 0 to +0.5 and back to -0.5. But why are we seeing a DC voltage of 10 volts on the output? Well, if we look at the thumbnail at the top, we see then that at 0 volts the transistor is not conducting. If we look at the bottom then, if the transistor is not conducting, then no voltage is going through the collector load resistor. I beg your pardon, no current is flowing through the collector load resistor, and therefore the remaining voltage, the full 10 volts, is developed at point B. So we're seeing a steady voltage at point B of 10 volts. And there we've highlighted the resistor. The resistor has no current flowing through it. If we now increase the voltage at point A to 1 volt, we see on the left-hand oscilloscope screen a voltage going between 1 and 1.5 volt, I beg your pardon, 0.5 volts and 1.5 volts. In other words, swinging around the 1 volt. But on the output at point B, we're seeing only half a waveform. In fact, slightly more than half a waveform. So what's happening here? Let's highlight these areas. Well, looking at the top thumbnail, we are on the highlighted part of the curve now. Because at the bottom end, at the input of 0.5 volts, we're not conducting. But at 1.5 volts, we are conducting. So, looking at point B, we're seeing that initially we have the full 10 volts. And as the transistor is driven into conduction, current will flow through the resistor on the load resistor, the collector resistor. And as current flows through that increasingly, then a voltage will be developed across the load resistor. And therefore, the voltage at B will go down. As the input waveform goes negative, it will decrease, as it goes further negative, it will decrease the amount of current flowing through the transistor, and therefore the voltage on B will go up. Until the voltage at the input gets less than about 0.6 of a volt, it'll switch off the transistor, and therefore the voltage at B will be clamped at 10 volts. So with the biasing set, around 1 volts DC, with a 1 volt peak-to-peak signal applied, the transistor is alternately conducting and not conducting, and therefore what you're seeing is the voltage at B representing only a portion of the waveform applied at A. If we then go to increase the voltage at A further, centering the voltage at 2 volts, now we're effectively on this part of the curve. We're always in conduction, and therefore you are seeing on the output the full swing of the voltage that's applied to the input. But notice that in all these cases, or at least in the second 2 cases, the output voltage is in antiphase to the input voltage. The output current is in phase, but because the current is developing a voltage across RC, the output voltage is in antiphase. Let's have a quick look at this then. This is the curve that we've been able to draw now for a while, with collector current IC on the vertical axis and base emitter voltage on the horizontal axis, and there's the curve. And you can see for this transistor, the knee develops slightly later than for the previous examples. It doesn't really move into being linear till perhaps 0.9 of a volt. So we talk about this curve having 2 parts, the nonlinear part, which is before the knee, and then the fairly linear part, which is after the knee. And on the right at the top of the screen, we've got a reminder of what the circuit might look like. Now we can superimpose on this graph what the collector, base current might look like. And there we have it there. We've drawn in blue base current, because for any particular VBE there will be a corresponding base current. So it's sometimes quite useful to have the 2 of them on one graph. Now this probably goes a little bit beyond what we have to understand for the advanced certificate, but it's good background nonetheless. If we apply the input signal to that graph, there at the top of the screen, we see a signal swinging between 0.9 of a volt and 1.1 volt. In other words, a swing of 0.2 volts on the input. And that will be driving a base current, if we look along horizontally, of approximately 1.8 volts up to approximately 4 volts. I beg your pardon, that's a base current of 1.8 milliamps up to about 4 milliamps. So we're saying that the 0.2 of a volt swing in VBE will give a corresponding swing in base current from 1.8 milliamps to about 4 milliamps. In other words, a VBE swing of 0.2 volts will give a base current swing of 2.2 milliamps. And let's see what that'll produce on the output. Well, if we draw off from the collector current curve, we see that we have a swing there of about 38 milliamps. And we know that beta is equal to IC over IB. So that gives us a beta for this transistor of about 17, fairly low, So we think this is probably a power transistor. And with the output signal, or the input signal being fully represented in the output, in other words, no clipping occurring, we can call this class A biasing, because it's all on the linear part of the curve. And the input signal's swing is not too great to drive us into the non-linear part of the curve, and certainly not into cutoff. If we had different biasing, such that VBE, the central biasing level, was about 0.6, as shown on the diagram there, we would have a swing on the base of between about 0.48 and 0.6, and for half or more than half the cycle, the transistor would be switched off, with only the positive peaks of the cycle switching the transistor on. And the corresponding output is shown there as just the little humps that manage to switch on the transistor, and we call that class C biasing. If we bias it up at around 0.7, for example, on this in this example, and we get the full half cycles in rather than just the peaks, so we have 180 degrees of each cycle, or the full positive peak of each cycle, we call that class B biasing. So we've looked today at class A, B, and C biasing. And we're going to go on further to look at biasing and biasing stability in subsequent videos. Thanks very much.